Today's lecture will be given by János Kollár from Princeton University, and the title is János.
Okay, thank you very much. So the title is Local Picard Groups and Descent of Line Bundles. So I believe this is not the title that's on the website, and I was very much surprised by the abstract that was there. No doubt I sent it, but I completely forgot about it. So, but I think that also has something to do with local Picard groups. So, okay. So then the starting point is, or points are the following three theorems. So the first one, maybe I think the earliest on this list, is a theorem of Boissier, Geber, and Sermon. Says that if there's a normal variety, well, then on it, of course, some divisors may be Cartier, and then there can be some divisors that are not Cartier. But they say that there are finitely many points, that if you have a divisor, any divisor D, then it's Cartier if and only if it is Cartier at these x sides. Yeah. So, sort of in principle, it could happen that there are lots of divisors there, so it can happen that they are all non-Cartier at sort of different random points. Okay, but the theorem says that no, it will happen only at just finitely many points. Okay. Now, then the second is a theorem that, well, so these authors, they proved more general statements. So these are a special case of what they have. So it's Batshotz and Kashini and Tanaka. So that it is a proper morphism with connected the fibers and is over FP. And if there's a line bundle that is trivial on all the fibers, then some power of it descends to X. So that means L to Q is obtained as the pullback of a line bundle from X. Okay. And the third theorem that is related more philosophically to this, though it can be viewed as a so there's something to do with it, but it's more just the general philosophy, if you think of it especially as the first theorem. So, again, it says if you have a normal variety X and you are looking at quasi-étal covers over it. So quasi-étal means that it's étal at all codimension 1 point, okay? And then we want to understand where can this ramify, yes? So, it ramifies at sort of some points of higher codimension, and these points a priori depend on Y. But again, the statement by Stibitz is that no, this will not happen, that there are only finitely many points, that if this morphism is étal at those points, then it's étal everywhere. So it's very much like the same, the first one, that various bad things can happen, but some of this is always controlled by finitely many points of the variety. And so the yes.
Do you consider only closed points, or you allow like generic points?
Oh, yes. So points are really points here. So that means not necessarily closed. Yes. Okay. And so
should I expect that if I remove these points, then the property is satisfied?
And so there is this problem that if points are not closed, then I don't know exactly what you mean by removing them. Yeah,
like a closed set containing these points.
And so for instance, if I look at sort of Stieglitz's theorem, okay, but of course, if you remove the singular set, yeah, then everything quasi étal is étal, okay, and so the question is, so if you are inside the singular set, but can it happen that there are morphisms that say, you know, that's ramified just at one point? Singular set is something like a curve. Can it happen that it ramifies at just finitely many points, and these points move if you move by? Okay. And so I think I have an example prepared about the first one. I will come back to it. Maybe that will sort of clarify this. Okay, and so then my aim is to do these theorems, or at least try to do these, the first two for arbitrary schemes. Okay, so then in the first case, I would like X to be an arbitrary scheme, and also in the second case, I would like X to be an arbitrary scheme, not necessarily over a finite field. Okay, let's see. So at least about the first one, the conjecture is very clear. So my conjecture is let X be a normal Noetherian excellent scheme. Okay. Then there are only finitely many points where the local Picard group is non-trivial. So I would like to come back to this. I will define what the local Picard group is. It is sort of the largest possible. There are various versions of local Picard group, and this is really the largest that you can have. Okay. Now, let's see, maybe here's an example that's sort of relevant. So let's look at the Whitney umbrella, okay? Now, this is not normal, yeah, this is singular along the z-axis, okay? And now the claim is if you pick an arbitrary point along the z-axis that's not the origin, then the local Picard group there is z, okay? And it's generated by what is a line that's passing things through this point, okay? So you see, so here that happens. Well, of course, we know that the problem is the singular set. It is the z-axis. That's the problem. But there, it is still there are these divisors that that hit the singular set at different points and are only non-Cartier there. Okay. So then in this case, it is not true that all the non-Cartian is caused by finitely many points. Yeah, of course, if you remove the singular set, everything becomes Cartier, but we are asking something slightly finer than that. Does this answer your question, Christopher?
Somewhat. I'll ask you more precisely later.
Okay, good. So then let's go ahead. Okay, and so now, as I said, that is my conjecture, and so there are here two things that I can prove, and I will try to explain this proof. So one is to prove the conjecture for normal varieties in characteristic 0. Okay, so there are only finitely many points where the étal local Picard group is non-trivial. Okay, and then in characteristic P, the proof works for normal Noetherian excellent FP schemes, but only up to P infinity torsion. Yes, so I can say that there are only finitely many points where the local Picard group is not P infinity torsion. I don't actually know whether this P infinity torsion is necessary or not. I find it very hard to understand P torsion in the Picard group in characteristic P. I just do not have a good handle of it. So there might be a counterexample to my conjecture where there are various p torsions coming in at various points. I don't know. Okay, so now let's see what is the definition of the Picard group. So let's start with a normal local scheme. Okay, so to start with just a local scheme of dimension at least 2, then the local Picard group is the group of rank 1 reflexive sheaves that are locally free outside the origin. Okay, so if you think of divisors, then you should think of divisors that are Cartier away from the point X and may or may not be Cartier at exactly X. So then in the algebraic case, it's very easy to see that this local Picard group is exactly the Picard group I get if I remove this point X from my scheme X. Now, so if I have an arbitrary X, so it's not local, and I have a not necessarily closed points, well, then I make it local. Yeah, so then I look at the local ring, then I take its spec, and then I get something local, and then I get the local Picard group. Now, then we would like to make it sort of even larger. So you should think of this definition so far as only Zariski local. If I have a closed point, then maybe I take the limit over the Zariski neighborhood. We get some group that's in general much larger if I take the direct limit of all the local Picard groups over all the étal morphism. So now, and I claim that this is in fact the largest sensible local Picard group that you can have. So there is a theorem of Artin that if you look at this group, that is the same as if you look at the strict Henselization, and then you take the local Picard group, and in fact, even if you complete it, so usually it is the largest just the Picard group you can get, that you first you take the residue field and you make it at least separably closed, and then you're looking at the completion. And so, but sort of these are all the same. And so it is clear that there are injections like this, but the fact that they are equal, that's a theorem of Artin. Okay. Now, so what's the difference between the local Picard group and the étal local Picard group? Here's a simple example. So let's look at the surface singularity. Let's start with X, Y, Z, and I add something that's general of degree at least 4. Okay. Now, then it is pretty easy to see that the étal local Picard group is C star times a finite group. So where do I get the C star? Well, just imagine that you blow up the origin. Then if you blow up the origin, the exceptional set will be these 3 lines, okay? And then if you think about it, well, this is a degree 3 plane curve, and so it's H1 is of OX is 1-dimensional, and so it is Picard group of that. So the Picard group was exactly this. That's exactly this. Oops. Okay. Well, I don't know what happens. I'm not particularly good, but there was this line here. So it's back. Okay. So then sort of this is, and now then there are some more singular points here I need to resolve this. So this finite group, it depends on exactly the P, Q, and R. On the other hand, my claim is that if this singularity sits on an algebraic surface, and local Picard group is finitely generated. So instead of getting this C star, I can get only some finitely generated subgroup of there. Okay, so what's the reason for this? Well, so that if I have a projective surface, then it's peak zero. That's always is projective. It's an abelian variety. And you see there is no morphism from an abelian variety to C star. And so that means that if I look at the Picard group of the surface and then map to this peak local 0 as 0, then it's always factors through the Néron-Severi group of the surface. So peak 0 gets killed. So the only thing I can get from here is whatever I get out of the image of the finitely generated Néron-Severi group. Okay, and so that means that étal local is really sort of the largest that you should look at. Okay. Now, so what's known about the local Picard group? So as sort of the same way that if you are over an algebraically closed field, and the Picard group of a projective variety is an extension of a, well, most of the time an abelian variety by a finitely generated group, the Néron-Severi group. We have the same structure theorems about the local Picard group. In the two-dimensional case, this was proved by Mumford. So there is a connected component and whose actually I think here is dimension is this exactly the R1H lower star OY, where this is a resolution, and it's not just the tangent space, but this is, I believe, the dimension. And here the discrete part is finite for surfaces. Now, if I'm in higher dimensions, so the right condition is, if you don't like this condition, just ignore it. Think of this example, X is normal and dimension at least 3. Okay, then the same thing holds as with the Picard groups. And usually there's a connected component, and the dimension of the Zariski tangent space is this. And now in characteristic P, of course, this can be non-reduced. So here it's really only the tangent space that can be non-reduced. And there's another problem here that I really would like to say, that as for projective varieties, the discrete part is finitely generated. And this is probably true, but we don't understand the P torsion sufficiently well. So we don't know whether that part is finitely generated or not. Okay, now let's try to deal with the non-discrete part first, and then I think so from here on I will be mostly in characteristic 0. And let's try to do something more general, to think ahead of the second the theorem that I try to generalize. So let's assume that I have a proper morphism, y smooth, x normal, and it has connected fibers. Okay. And so then the first claim is that the torsion in R1 G lower star OY depends only on x, you see. So if y is just a resolution, then this has been known for a long time, and it's not hard. I mean, that's sort of the main part, but here it can have some large dimensional fibers. And so R1 G lower star OY, of course, it depends on the choice of y, but the torsion inside it depends only on x. Okay. Now, and then, well, so where are its associated primes? Okay. Well, there is none in codimension 1. That's relatively easy to see. And then there's nice thing coming up, that if you are in codimension 3, then the length of this supported at x is exactly this H2XOX, which by Buteau was exactly the tangent space the local Picard group. And then if we are in codimension 2, so then this is not the tangent space to the local Picard group, then I get exactly what I get out of a resolution of singularities, okay? So then although these two statements about the dimension of the tangent space, they were different here, this formula actually completely unifies them, okay? So that means that the torsion in R1 G lower star or Y at various points exactly tells me the tangent space of the local Picard group. So we have the first finite statement. Well, this is a coherent sheaf, so it has only finitely many associated points, and these are the only points where the local Picard group can have positive dimension. Okay, so at least the non-discrete part is now taken care of, and now let's try to pay attention to the discrete part. Okay, and so now I will start with the closed points over C. This turns out to be technically easier. So once you understand the non-closed point they behave essentially the same, but there's a technical issue that I sort of switch to the complex analytic case, and you cannot localize at something like a complex variety at the non-closed points. So really have to pay attention to the topological structure. Okay. And so let's assume that I'm looking at a point where this étal local Picard group is discrete. And now there are two statements that I would like to prove. And so one is that I can take the Chern class map. This is the link, okay? So what is the link of a point on a complex manifold? So there is this manifold, a point intersected with a very, very small sphere, and see what you get there, okay? So and now then of course that if I have something here that's a line bundle sort of nearby, I can restrict it to the link, and then I can take its Chern class, okay? And so this is exactly the Chern class map C1, okay? And now my claim is that this map is injective. And there will be a similar claim if I have the proper map. Then, well, I will explain in sort of more detail what this map is. It's not that completely obvious. Actually, I sort of need to take the quotient by here. So anyhow. But I sort of get a similar map that again the local Picard group and an H upper 2 of the fiber. I mean, you should think of this fiber and the link as in some sense closely related. Okay, and now here I just say that the kernel is only torsion. Okay, so now let's try to focus attention to this part 1. Okay, so let's see. So that then I start with this capital X, and there's a point in it, and the intersect with a small ball. So I have a small neighborhood of it, say that is Euclidean neighborhood, and then the boundary of it will be the link. Okay. Now then, first I claim that the étal local Picard group of X is the same as the analytic Picard group of X. Okay. Well, you sort of could think about it as something smaller than the completion. So a priori, the completion can have even more line bundles, and so the theorem of Artin, I already said that the étal local Picard group is the same as analytic Picard group. So then I just look at the holomorphic coherent sheaves on U that are locally free outside X. Okay, now then, so strictly speaking, this step is not exactly needed, but to think about it, it is very good that the analytic local Picard group is the same as the Picard group of the complement, if U has dimension at least 3. And so you see that if you think of algebraic geometry, then this was an obvious statement, because if I have a coherent sheaf on U minus X, then the push forward of it to U is automatically coherent. But this is not true complex analytically. So if the dimension of U is actually 2, so maybe just to say, so okay, so the analytic Picard group of C2 minus the origin is infinite dimensional. Okay, and so, well, of course, the local Picard group of the origin is C2. It is just trivial. Okay, so that means that here is C2 is important exactly. CU says that as soon as the dimension of at least 3, I can switch from the local Picard group to the Picard group of U minus X. Now, then another thing I can do in complex analysis is I have the exponential sequence. So the constant, this map probably should be think of multiplication by 2 pi I, and then this is the exponential map. And then if I take its cohomology, then I get this. So that the Picard group of U minus X, it sits inside the H1 of U minus X, the coherent cohomology of U, and then here comes the topology in, and this map is the Chern class map. Now it's a relatively easy comparison of cohomology groups, that these two are the same. So then the H1 of U minus X is the same as the second local cohomology of XOX, and we assume that this is zero since we are in the discrete case. Yeah, so exactly when this is non-zero, that is a non-discrete case. So that means that this Chern class map is now an injection, but then this U minus X, it retracts to its boundary. So this U is essentially just a cone over where this LX. So once I move the vertex of the cone, then it retracts onto LX. Okay, so then I have this injection. Okay, now, I mean, as I said before, for non-closed points, I will need some more work, but so this is essentially the argument. Okay, so now that we need to prove that the H2 of the links is trivial at all but finitely many points. Okay, well, so again, I need to use the complex analytic structure. If you have an arbitrary algebraic variety, complex variety, then it has a Whitney stratification. So I want here the dimension Wi to be I, but I don't assume that it's irreducible. So, you know, if I have lots of I-dimensional pieces, I just put them together into this Wi. That has the property that if you take a point in X and you look at a small neighborhood, then it's homeomorphic to Ci. So these are the direction that you move inside Wi, and there is the transverse slice. Okay, so again, if you want a picture, so for instance, if I have a cusp times a line, then sort of if this, then maybe this will be my W1. And then if you have a point here, then there's a C factor here. So that's the C factor in this direction. And there's a transverse direction, which is just this. Okay. And so then this is then the picture. And now there is a lemma that if you are inside one of these factors, then the H2 of LZ is 0. And so let me actually do this in an example of a lower dimension. Okay, So the question is sort of where do I get some more triviality by these factors? And again, I sort of want to, I'm down here dimension. And so let's assume that I just have something where the link is just, so for instance, if I'm just inside C, okay? Well, then the link is S1, that is not simply connected, okay? But what if I go to C cross C, okay? Well, then a neighborhood will be, okay, then a neighborhood will be something like this. And so then the link is what? So I have the tube. Yeah, so before I had a circle, and now I have the tube out of it. But now I put in these two caps, okay? So then this became now an S2. So then before I did have a pi1. So here the pi1 was Z, and then I just, well, so here I only took, I mean, not by C, but by R, okay? Yeah. And so then, so taking the product with R, that was enough to kill H1. And so now you can imagine that taking the product by C is enough to kill H2, okay? And so now this means that if I have a Whitney stratification, then this H upper 2LZ, this is trivial except at the finitely many points of the zero-dimensional strata, okay? So this means at least for sort of closed points, this takes care of the theorem. Okay, now let's have now this, okay? So well, recall this theorem, Caccini-Tanaka, that if I have a proper connected fibers over FP and there is a line bundle that's trivial on the fibers, then the power of it descends to X percent, okay? So now I would like to prove this for arbitrary scheme. So the aim is to sort of get rid of this FP, okay? And so now then, of course, I would like to do that. There's sort of one problem with this, that it's not true, actually, okay? So the statement that the line bundle is trivial on fiber saying that it descends, it's actually not true in characteristic 0, okay? So we need to do something more complicated here. And so not just remove references to FP. And so that here is my conjecture that I actually hope that works. So that again, I start with the same thing. So the smoothness is probably actually not necessary. So yeah. And so I believe the smoothness is actually not needed, but maybe XY normal, okay? So then I have this, again, I have a proper morphism with connected fiber between, say, normal scheme. Now, then I would like to say that there are finitely many fibers, sort of such that, well, such that this sequence is exact. So then I have something, the line bundle on X, I can pull it back to Y. And if I have a line bundle on Y, I can restrict it to, well, not just the fiber, but maybe the M's infinitesimal neighborhood of the fiber, okay? And so you see sort of before that, what I did, I took a line bundle here and I restricted it to all fibers. And then we said, well, then it descended. Now, well, and this is not true if we are in characteristic 0. So then I would like to say that, well, so maybe I take some infinitesimal neighborhood of the fibers, but I want to take only finitely many of these. So I say that there are finitely many sort of badly behaving fibers, or maybe unpredictably behaving fibers. And if I take care of it, then I have descent. Okay? And so then this is the conjecture. So let me make some comments. And so you know, if you have any proper per scheme, then, well, of course, if you have a line bundle in it, you can restrict it to the underlying reduced structure. And it was proved by Grothendieck that the kernel of this is just unipotent. So that means that if we are in characteristic P, rather unipotent is in fact P infinity torsion. Okay, so that means that this conjecture would definitely imply that characteristic the P statement that if something is trivial on the reduced fibers, then some power of it descends. Okay, so we sort of had to make some change to the statement here, but aside from that, it should work. Okay, now then maybe I should have said this before, that of course the formal function theorem says that if you restrict to that you look at all points and so all neighborhoods, then this map is exact. Yeah, so at least for sort of line bundles, the statement of the formal function theorem is precisely the exactness of this. And so then the claim, or maybe the new aspect, that there is this doubly infinite sum here, and in fact I hope that a finite sum is enough here. Okay. Well, and now, well, then of course you might ask sort of, well, which are the points that I need to take? So can I actually decide in advance what are these points, and then what are the numbers? Okay, so now let's take the stronger form, and in fact this will be no a theorem, but again only in characteristic 0. Okay, so once I'm in characteristic 0, then of course the smoothness is sort of no problem. I can always resolve by. So that sort of doesn't matter much. And so again, and so I have this apropyromorphism with connected fiber Y smooth, and then X has to be normal. Okay, and so the main part of the statement is sort of this, where I tell you sort of which points I need. Okay, so first of all, there are some points where I need to use a higher order infinitesimal neighborhood. And I say that these are precisely the points where the local Picard group on X is positive dimensional. Okay, so you see an interesting feature of this, that this part only depends on X. It does not depend on Y at all. So the bad points that I have, they only depend on X, on the target, and in a very clear way. Okay. Now, for the other points, I need to work only with the reduced structure of the fibers. I don't even need the fiber. The fiber itself, of course, might have a non-reduced part. Yeah. And again, I can tell you exactly which are the points I need. Well, I need the points where the local étal Picard group is non-trivial. And then, of course, I need the generic point. And then I need the point where the fiber has an extra divisor. I will explain it on the next slide in a moment. I want to point out another thing, that this is not just for X, but so that once I have these points, then the sequence is exact after any possible étal base change. Okay, so So that's a rather strong form that I know exactly which fibers I need, and I know most of them I need with reduced structure. Now, one problem I have that I don't know how to compute M at the moment. So I hope there will be something like a clearer formula for that, or at least an estimate. But at the moment, I don't have a sensible way of sort of figuring out M. Okay. So let's see. What do I have? Yes, and so what are these extra fibers that I need? Okay, so here is my target. Okay, maybe let's say it's a surface, and then there's a mapping down to it. Yeah. Okay, so now sort of what can go wrong? So for instance, if I have a point here that I just blew up, okay, so then I might have a surface here. So might have a divisor here whose image down here is smaller than a divisor. Okay, so then here's a divisor here mapping to something smaller. So I definitely need these points, okay, because for these divisors I need to account for those divisors. Okay. Now, then other thing that can happen in the one-dimensional degenerations. So if I'm just looking at codimension 1 point, then at some point, for instance, if the fiber becomes reducible, okay, well, then I definitely need this. So if it's reducible, then I need this point. And it is actually, it's sort of more complicated for me when the fiber becomes multiple, yeah? And so I still sort of need this point. But as long as the fiber stays integral, I do not need that point, okay? So sort of this is then the statement, what it means that the fiber has an extra divisor. Okay, so let's see. Okay, now 2 comments that, well, in fact, this I union J, that's the smallest possible set that works. So this is really, if you take any smaller set, then at least for some choice of the étal U to X, that sequence will not be exact. Okay, so this is really optimal as far as the choice of this. Now I already mentioned is that, so the M, but the good part is depends only on X, but I don't know exactly how to compute this. I hope there will be something that is sensible out of this. Okay, so now again, so how to prove this? Well, it's so the basic outline is very similar. So again, I have some étal local Picard group, and then I want to end up in some second cohomology group by some Chern class. Okay, so what do I do? Okay, so then I start with my setup here. And now, well, and so then if you just write down the Lurie spectral sequence, then it says the Picard group of X maps to the Picard group of Y, and that maps to the H0 of the R1 G star OY times. So this is the multiplicative sheaf. Okay, so what you have to pay attention to that this is not a coherent sheaf. Okay, so that creates various headaches. So you have to think through various theorems that you are sort of used to. Okay, so then we need to compute this, and then again you can look at the exponential sequence on Y, and you just push it forward. So then you get this long exact cohomology sequence, where here is the R1 G lower star OY times, and then, well, this is just something relative version of the second cohomology group. So we are completely happy with this term here. Now, we are basically happy with these two terms. So this here is a coherent sheaf, and then here this is a constructible sheaf. And so you see sort of this is the thing that sort of makes this sheaf more complicated, that we are happy with coherent sheaves, they have a good theory, and we are happy with constructible sheaves, they have a good theory, but here the two need to be mixed together. Okay. And so this means that if I look at this map from the Picard group to this H up R2, I mean, if I localize it enough, then what I'm interested in is the sections of these quotients that are supported at X, okay? So then it's exactly this map. I look at the quotient that goes into this. Now the question is, well, how can I get a section of this that's supported at X, okay? But so the first way is, well, of course, that this coherent sheaf might have a section that's supported at X. Okay, but I understand this is exactly the non-discrete case, okay? So yes, if it's non-discrete, then things are more complicated, and this injectivity, or rather the kernel distortion, I claimed, is only in the discrete case. So that means I don't have to worry about this. Okay. Now, maybe what else can happen the best is if I just give you an example. So let's assume that this R1 G lower star OY is just OX. It can happen. And now here, what would be a bad constructible sheaf? Well, I just look at the constant sheaf outside the point X. So that's just the constant sheaf on X minus the point X. And then I just extend this by 0. Okay. Now you see, this would be bad, because then here I have the constant 1 section, which becomes 0 outside the point X, but is not 0. Okay. So then this would be something that's in the kernel and it has infinite order. Okay. And so that means that I need to show that this situation and anything like this cannot happen. Okay. And now this turns out to be case, but it's a fairly big theorem. It's called the invariant cycle theorem. Okay. So something like this does not happen, at least with Q coefficients. Okay. So okay, maybe yeah. Okay. So oops. And so then I need that at least with sort of Q coefficient, this does not happen. Now, in the one parameter version, this is known as the Clemens-Schmidt sequence. But unfortunately, I need the higher dimensional version, where this is the special case about the theorem of Beilinson, Bernstein, and Deligne, that these sheaves, they decompose into section cohomology complexes. Okay, and so this means that, so that's why we get in the kernel some possible torsion, because this theorem, so the theorem is really needs Q coefficients. Okay, so up to torsion, this is not exactly right, sorry, this is okay up to torsion, but sort of not without it. Okay, and now so on the one hand, this is good news. On the other hand, this is a really big theorem, yeah, and this needs actually the complex structure. So even for characteristic 0, row schemes, I don't know what to do with these points. So somehow I would need something like the invariant cycle theorem, but I sort of need only for R1, which is probably the easiest, but still I just don't see what to do at this point. Okay. Now then, maybe I just want to mention, so that once you have this, of course, we would like a numerical version of the push forward. And so that's the following. So again, I have my usual setup here. And then, well, let's assume that X has rational singularities, or at least one rational singularities. So if you haven't seen what one rational, at least you take a resolution, and then you are only assuming that the R1 H lower star OX prime is 0. So rational means that all the Ri's are 0, R1, R2, R3, and so on. So one rational means that only the first one is 0. And now then, the claim is equivalent that some power of L descends, or L needs to be just numerically G trivial. So as degree 0 on every curve that's contracted by G. And of course, some power of it should be trivial on the generic fiber. I mean, I need to assume some kind of triviality on the generic fiber. And now, so this is actually not hard. Maybe the interesting observation is that one rational is strictly not necessarily, that if X does not satisfy the one rationality condition, then this theorem does not hold for one Y. Maybe after an étale base change. So maybe not necessarily in X, but after an étale base change. There is actually a Y where this fails. So that sort of, in some sense, this really tells me sort of when is descent just a completely numerical condition in characteristic 0, just the base must have these one rational singularities. Okay, now in characteristic P, well, so the results are much weaker. I have much less control over the points that I need, and then I also use here the theorem of this BSCT. So you know, I mean, it's not really a generalization when you are sort of using it that much, but at least for now I use it, and I said I have no control over the P infinity torsion. And then, so again, let me just mention that the result of Wittaszek that should imply that they imply that there's an obvious mixed characteristic version. So it's again, it's not as nice, because in characteristic 0 I can prove things only for varieties, and so not schemes, but for things that are, say, finite type over Z or something like this. There's a nice statement. Okay, let's see. So since I have a little more time, maybe let me outline this the proof of the whole starting point, theorem of Boissier, Geber, Sermon. At least here the key steps. So once you have these, you just basically have to mumble Noetherian induction or something like that, and it works. And so what we want to say that if I have a normal proper variety, and then I have a subvariety with generic point eta z, then I say that there is a dense Z0 inside Z, such that if a divisor is Cartier at this eta Z, then it's Cartier along Z0. Now you see, if I fix my D, well, then of course I know if it's Cartier at the generic point, then it's Cartier in a whole open neighborhood. But the interesting claim is that this neighborhood, that is Z0 I can choose, it does not depend on D, so that I can make a uniform choice. Okay. So then first I have the Néron Severi group, and that's a finitely generated abelian group. So here I use that it's a normal proper variety. Now let's look at the subgroup of the Néron Severi Descartes at eta z. Okay. Well, it's a subgroup is also finitely generated. And so that means that I need to only sort of throw away the subvarieties where these DIs are not Cartiers. Once these DIs are Cartier, then everything is okay. So actually, probably sort of this part should have been sort of after this, but anyhow, okay. So then, I mean, clearly the important thing is sort of here how to deal with the connected component of the class group. And now it's here that I really use that the connected component of the class group is just the pullback of the Picard group of the Albanese variety. Yes, so there is this map from X to its Albanese variety. I mean, if you have a point, then this is the universal map from this X to an abelian variety. And then if I have a numerically trivial line bundle here, I can just, of course, pull it back. And now, maybe this A up star L. So, well, I don't know that it's a line bundle exactly because this map here, it is not a morphism everywhere. It's only a rational. Okay. Okay. Now, but then. Well, it's rather clear that this Albanese has a maximal quotient with the property that if I look at this composition, then this is defined at the point eta z. And so it is just a formal thing. I just look at sort of all of these things where it's defined. And if I maps to 2, of course, maps to the fiber product, actually the product. So this is just a completely the formal statement. Now here you need a little bit of argument that the subgroup of the connected component of the class group that are Cartier at eta z, this is exactly the pullback of the pick 0 of the Albanese of so this modified Albanese map. But so once I have this, then you see then this open set will be is precisely where this Albanese map is defined. Yeah, so it's defined at eta z, so it's defined in a neighborhood, and then of course the backs are all locally free at those points. Okay, I think thank you very much.
Any question for János?
Sorry, I have a kind of, maybe this is an unreasonable question, but I was just wondering, is there any hope of proving the numerical version that you had in Q60 by like spreading out?
You mean to the characteristic P? And so it is possible. So now, of course, in characteristic P, you have descent without assuming that the base has rational singularities. Yeah. And so I think if you can somehow prove that this exponent we need, that this is controlled independent of P or something like that, then it should follow. Yeah.
Right.
Yeah. So I think if you can prove that in characteristic P, the line bundle itself descends, yeah, that if it's trivial on the generic fiber, yeah, that if it's trivial on all fibers, then it descends. You need, I think then it would work. Yeah. So I mean, I certainly I hope very much, so one reason I gave this talk, because I'm sort of stuck with this, that, so, I have it over where C, and then it comes out of what the UN Koshini Tanaka did in characteristic P, but somehow there should be a more general statement. So, if you have ideas, I would be very happy to actually hear them. How can one actually fix this up better?
Any other question? So if no, let's thank János again. And if you go see the chat, there is a link for the gatheroton, which is for the social activity. Okay, I will probably see you in the gatheroton.
Okay, thank you.